In this video, we're going to talk about light. We're going to get an introduction to quantum theory. I used to call this light physics for chemistry, but we're going to not deal about that. All right, some of this you may already know, some of this may be new. This isn't a huge focus. I want to get us some background before we dive into some more quantum-y stuff that's more important. Okay, um, so light is essentially electromagnetic radiation. We kind of use those terms interchangeably as we think about stuff. So when we talk about electromagnetic radiation, there's two components to this, and one of those is an electric field component, and one of these is a magnetic field component, and they run as waves perpendicular to each other, right? You can see that here, right? The electric field goes this way, the magnetic field is this way, okay? Some things we want to think about when we talk about this. When we're thinking of waves, we can measure waves and deal with waves and talk about waves using things like amplitude, which is the height distance of a wave like this guy, and wavelength, which is a distance between two peaks. Okay, wavelength could be really any distance as long as it's the same point on two adjacent pieces. So we could do the tops, we could do the bottoms, we could do the middles, okay? And wavelength is given the unit of lambda, which I kind of write like this usually, okay? Yeah, okay. Some other properties here we can think of, the different wavelengths of light of magnetic radiation are going to change the colors, especially in the visible. We'll be able to see the different colors because the different wavelengths have different colors. Okay, when we get outside of visible, they still have different properties and stuff. We just can't see them with our human eyes. Um, Different amplitudes is different brightness. So you can think about this as the volume or the intensity, like volume of sound, intensity of light is from the amplitude. So a lower amplitude is dimmer and a higher amplitude is brighter. Speed of light, we relatively treat this as a constant. Um, it is a constant as long as we're in a vacuum, and in air, it's roughly the same idea. We call this the constant of C, and this is 3.00 times 10 to the 8th meters per second. You may see slightly different numbers in different areas as we talk about things, but they're all roughly 3 times 10 to the 8th meters per second, and we use them accordingly. So speed of light is really fast. There we go. Okay. Okay. Oh, wait, let me go back. Okay. Other things we can think about is frequency. I don't know why I don't have a slide about frequency, but here we go. Frequency is how many wavelengths pass a given point in a certain amount of time. Okay, usually it's 1 second. So we can also think of this as cycles or waves per second. Okay, this has a unit. It looks weird. This has a unit of seconds to the -1, which is the same thing as saying 1 over seconds. Okay, so if we said that has a frequency of 500 seconds to the -1, then this is the same thing as saying, as saying 500 over seconds. Okay, it's weird. It's saying 500 things go by in a second. Okay, it's neither here nor there. Sometimes you see this represented in hertz. Hertz is the same thing as a inverse second. Okay. Additionally, we can relate the wavelength and the frequency together by the speed of light. So the frequency, which gets this little symbol nu, Greek letter, okay, it looks like a fancy V or a sloppy V when I write it. Frequency equals the speed of light divided by the wavelength. Okay, so we'll use this together, right? This is going to be meters per second. This is in meters, and so this becomes seconds to the -1. So the units work out, okay? Next up, let's think about electromagnetic spectrum. So there's a whole wide variety of, well, there's a giant continuum of what wavelengths and frequencies are possible for EM radiation. And this is things we've come to know. What we see in the visible spectrum is just a small portion of this here in the roughly just left of center, assuming this is to scale, okay? So it's a very small portion. What I kind of want us to get here is, you know, that wavelength and frequency are inversely related, okay? And we'll see in a second that energy is related to this as well. So a high frequency, think of it this way, a high frequency is high energy. It's also a very short wavelength, okay? And the inverse is true too. So this is why things like we have radio waves are everywhere. You go outside, right? This is why you're driving around, you can pick up radio stations because they're broadcasting just radio waves out into everywhere. Okay, you're surrounded by radio waves all the time. It's not that big of a deal. Okay, visible light, it's not that big of a deal. Ultraviolet light, this is why you get a sunburn. It's higher energy, it's cooking your skin. Okay, X-rays, they have high energy, they go right through you, right? Gamma rays, even worse. So you can think of things along those lines as we do it, okay? So we also want to think about knowing the order of the spectrum, which we've probably known this since kids, right? This is violet to red. All right, red is long wavelength, violet is short wavelength. So violet has a high frequency and red has a low frequency. Okay. One of the properties of waves that's going to be very important for us throughout the course is interference. Okay? And this has to do with how two waves interact with each other. Waves that interact, what we say in phase, where the two, right, where the the peaks line up and the valleys line up. This is called constructive interference. And what that does is it's literally adding the waves together because the two high points and the two low points are at the same spot. Okay. If they're out of phase, then the high spots and the low spots are not lining up with each other. They're lined up backwards or wrong, or however you want to think about it. This is essentially subtracting the waves. And so we have destructive interference where there's no wave left. Okay. You can kind of see this here in this thing. This is a continuum depending on how in phase or out of phase the waves are. We're just looking at the two limits of this, right? The most constructive and the most destructive. Okay. One thing important to notice about waves, and light does this, okay, is that what we call the double slit experiment. And we'll circle back to this in a bit too. That, what am I thinking? Sorry. So like here, this would be like, you know, a front of a wave coming at us. And since this would be more like a water wave, you can hit here and then the water wave curves out as you go, diffracted out. If you have a light source, then the waves are a little bit curved when you start, okay? And when you hit the double slits, each slit starts a new wave front, okay? And the difference between the two sets of waves here becomes apparent because they start to have constructive and destructive interference. And so you see white light spots and dark spots because the difference in amplitude of the diffracted waves interacting with each other. This will be important later on, but this is a very wave property to be able to do this. Okay. All right. So quantum theory really started around in the early 1900s, and I guess the best place to start with this is black body radiation, which it sounds weird. There's a lot of physics behind this. We're not going to stress about it. But any object that's heated will emit light. This is why we get light from the sun. Okay, the sun is super hot, so we get light from the sun. Okay, right? If you have your hot stove, you can actually see the burner is glowing, and that glowing is black body radiation. Okay. What's important about this is the amount of energy that's given off at a temperature depends on the wavelength of the emitted radiation. Okay. So a lot of, and you'll see this if you go like shopping for light bulbs and stuff, like they'll say, oh, well, that's a 5,000 K light or a 6,000 K light, just meaning how much intensity is coming out at that particular thing. It's like the temperature of the light. Okay. And what came through with this at the time was right. So it only depended on the wavelength of the light. And so Max Planck, or Planck, I guess, kind of defined this as a quantum of energy, meaning that at the higher temperature, you had more packets of light. Okay. And what he said was you could define a packet of light by an energy that was related to h times the frequency. H here is called Planck's constant. I don't know if you can read that because I wrote it under my video. It didn't even show up. And now there's puppies. Okay, let me go back. Constant. Okay. Sorry. Really what they saw in the black body, what Planck saw in the black body radiation, was that the energy of the light was always emitted as a whole number multiple of h times nu. Okay, h is called Planck's constant nowadays, and this is 6.626 times 10 to the minus 34th joules times seconds. Okay, it's very, very small because light is very, very fast, and so we'll worry about that. Okay, and so what he's defined for us here is the idea of quantization. We only have whole numbers of h nu energies available to us in the black body radiation. Okay, and this is perplexing, but what I want to get at is this idea of being quantized. Okay, that's where these puppies come from. So things every day that we know are quantized, right? It just means that only just certain values exist, right? Like on a stairway, the height on the stairs is quantized. You can only step on certain stairs. You can't stand in between the stairs because gravity is going to pull you down to the next stair. Puppies are quantized because you only really birth a whole puppy, right? You can have 4 puppies or 3 puppies or 2 puppies, but you can't have 1.5 puppies. So, or it's gross to think about 1.5 puppies. Music notes on a piano, you can only press keys that are there. Laying an egg, you only really lay whole numbers of eggs. So 1 egg, 2 egg, 3 eggs, a dozen eggs. We talked about dozens of eggs. Okay, that's what we mean by quantized. So what Planck said was that energy is quantized. You only get certain values of energy, and those energies are whole number multiples of Planck's constant times the frequency. Okay, and this was helpful because this was 1905 now with Einstein. I don't know why I didn't write Einstein on here. Einstein was looking at the photoelectric effect, which was moderately baffling. Okay, I have a YouTube link here for a more detailed description of the photoelectric effect because this is one of those things that I'm just like, yeah, whatever, I'll accept that it's true, but we'll let someone else handle the nitty gritty. Essentially, in a photoelectric effect, if you shine light on a metal surface, the light will eject an electron out of the atoms on the metal surface. Okay, this has a lot of interesting uses as far as technology goes, but it really wasn't understood too terribly much. What they knew was that the light had to have a minimum frequency in order to eject an electron, which they called the threshold frequency. And then now Planck has said, well, the threshold frequency, the frequency is going to relate to the energy. So there's some sort of threshold energy to do that. The number of electrons that are ejected is not related to the energy of the light that you give it, but it's related to the amount of light that you get it, the intensity of the light. So as long as you have the threshold frequency, If you make the same frequency and shine it brighter and brighter and brighter, you're going to get more and more electrons ejected off. And so all of this was perplexing. They knew all this data. And it wasn't until Max Planck and his black body radiation stuff decided that Einstein kind of figured out that, oh, well, if the light can only have quantized energies, then that's partly probably why we can do this. And so he coined the term a photon for a quantum of light, or a light particle. It's weird, right? Okay. And he said the energy of that photon was equal to h times the frequency, which we've just seen that. Okay. For an electron to be ejected, the photon must have at least enough energy to break the attractive forces that are holding the electron in the atom in the first place. Okay. And all of this is building us up into what we're going to talk about later on in quantum mechanics. Ooh, okay. So that's that. I'm sorry if that was awkward. Let me know if you need anything, and I'll be here.